Hello students, in last class we already discussed about what is center of mass, what is moment of inertia and what is rotational motion. So in center of mass we already discussed that center of mass is an imaginary point where total mass of a rigid body is supposed to be concentrated. The point or the center of mass may be inside the body or may be outside the body. For example, for ring the center of mass is outside the body, but for a disc the center of mass is within the body or at the center of the disc. Clear? So center of mass is the imaginary point where total mass is conserved. Then we discussed what is rotational motion. The motion of a rigid body is said to be rotational motion if each and every constituent particle of the body executes circular motion in different circular path with constant angular velocity. Then the complete motion of the rigid body is said to be rotational motion. Then what is moment of inertia? So moment of inertia of a particle is defined as what? If here is a particle of mass m which is rotating about an axis, the perpendicular distance of the particle from the axis is r, then the moment of inertia of this particle about this axis of rotation is how much? Defined as mr square. So if there are large number of particles, we have to add them individually by calculating mr square. Clear? And what is radius of gyration? If for a rigid body there are large number of particles and the moment of inertia of complete body is given as mr square, or this can be written as m1 r1 square plus m2 r2 square and so on. So instead of calculating the moment of inertia of each individual particle, we have to calculate the moment of inertia of the body in such a way by multiplying the distance from a point where the total mass of the body is supposed to be concentrated. Let this is the point, and the distance of the point from the axis of rotation is known as what? The radius of gyration. So we can write total mass of the body into square of the radius of gyration is also equal to moment of inertia of the body. So from this we will get what? The radius of gyration k is equal to I divided by m under root. Okay, and we already derived the moment of inertia of a ring which is given as mr square about the axis which is passing through its center of mass. Then we find out the moment of inertia of the ring about the diameter which is mr square by 2, then about a tangent which is parallel to its diameter which is given as 3 by 2 mr square, then untangent which is perpendicular to its plane and parallel to the axis which is passing through the center, and its moment of inertia is how much? 2 mr square. Clear? And we already discussed the two different types of theorem, that is one is parallel axis theorem and other one is perpendicular axis theorem. These two theorems are very important to find out the moment of inertia of different bodies. Clear? So what are the moment of inertia of different bodies? You have to remember that for a disc the moment of inertia same as that of, if this is a disc, this is, I am writing some moment of inertia of some geometrical object about their own axis. What is own axis? The axis which is passing through the center of mass of the object and perpendicular to its plane. So moment of inertia and the body. So if it is a ring, its moment of inertia about its own axis is mr square. If it is a disc, its moment of inertia about its own axis will be mr square by 2. Okay, I am drawing the figure. This is the ring and this is the axis. Here this is the disc and this is the axis. Then cylinder, hollow cylinder. Sorry, its moment of inertia will be same as that of ring, that is mr square about its own axis. So if this is a hollow cylinder about this axis, then solid cylinder, that is mr square by 2 where r is the radius. Here r is the radius and mass is m in each case. So this is the axis and here the cylinder is solid, mr square by 2. Then sphere, hollow sphere, it is 2 by 3 mr square about this axis. mass m, radius r. This is a hollow sphere, and if solid sphere, this is 2 by 5 mr square about this axis. Okay, so you have to remember this standard moment of inertia of some geometrical bodies about their own axis, and by using parallel axis and perpendicular axis theorem you can find out the moment of inertia about any other axis. Clear? So next we are going to study about torque, denoted by tau vector. Okay, what is torque? As force is a physical quantity which is cause motion in linear condition, same is the term torque in case of rotational mechanics. Clear? As force is the physical quantity which is responsible to create motion in linear motion or rectilinear motion, same is the torque which will produce rotational motion. Clear? So force is required to produce or generate linear motion, torque is required to produce rotational motion. Clear? So what is force in case of linear motion? The same is torque for rotational motion. Clear? So torque can be defined as, it can be defined as the product of magnitude of applied force and perpendicular distance of point of application force from axis of rotation. Okay, for example, if here is a body or particle and I am applying a force at this point into the plane, and the particle will rotate about this axis, then the distance is r. So here I can write the torque is equal to r into F. Clear? Because F, here F is into the plane, the force acting at this particle P is into the plane, so F is into the plane, and this is the axis of rotation of this particle P, so the force is into the plane and the distance of the force from the axis of rotation is r. So tau is defined as the perpendicular distance from point of application, that is r, into the magnitude of force, that is F. So tau is defined as Rf. Clear? Or we can write it also as the torque about an point is defined as the cross product of position vector, the torque of a force, the torque of a force. Okay, the torque of a force about a point is defined as the cross product of position vector of the point of application of force with respect to the point about which torque is to be calculated. and the applied force. So we can also define the torque of a force about a point is defined as the cross product of the position vector of the point of application of force with respect to the point about which torque is to be calculated and the applied force. For example, if I am applying a force along this direction, okay, on this point, and this is the point of application of force along this direction. So if this is the point where the force is applied along this direction and I want to find out the torque of the force about this point, so the point of application of force is along this direction, so this is the direction and this is the position vector of point of application of force. So the cross product, this is the r vector, this is the force, so the cross product between r cross f will give us what? The torque. So at this point, this is the direction of r vector, this is the direction of force vector, because this is the point of application where the force is applied, and this is the point O about which I have to calculate the torque. So tau about O is equal to how much? R vector cross F vector. Clear? Or in this case, if I am considering the perpendicular distance of the point of application of force or the perpendicular distance from O to this point, so if this angle will be theta, this is also theta, so this is the perpendicular distance from the point of application of the force. So we can write it will be as what? If this is the point O and this is the position vector, and here I am applying the force along this direction F. So let this is the direction of R. If this angle is theta, so the perpendicular component of R to the direction of force, or the torque will be the perpendicular component of force to the displacement or position vector R. So if this is F, this angle is theta, so this will be the F perpendicular, which is equal to how much? F sin theta. So here also tau can be written as Rf sin theta. Clear? So we can write torque is equal to R cross F or Rf sin theta. Clear? So torque about a point or the torque of a force about a point is defined as what? The product of magnitude of applied force and the perpendicular distance of point of application of force from the axis of rotation. Or the torque can also be defined as about a point as the cross product of position vector of the point where the force is applied to the applied force, or by magnitude we can write this is the vector form. Okay, tau vector is equal to R cross F, or by magnitude we can write tau is defined as the product of perpendicular distance, that is R sin theta, with magnitude of force, or the perpendicular component of force to the position vector R. So in this case I am taking the perpendicular component of applied force, that is F perpendicular, which is F sin theta, because this is the angle between F vector and R vector. So it will become tau equal to Rf sin theta. Okay, so we get torque is equal to Rf sin theta or R cross F in vector form. Clear? So how to find out the direction of torque? Here torque is a vector quantity and it is the cross product of position vector and applied force. That's why the direction of torque will obtain by using right hand thumb rule. If I am crawling my finger along the direction of R cross F, as in this case, this is the direction of R vector, this is the direction of F vector. So if I am crawling the finger of my right hand along R cross F direction, so the thumb shows outward, so the torque in this case will be out of the plane. Clear? So we can get the direction of torque by using right hand thumb rule. If the torque is out of the plane, then it is taken as positive. If the torque is into the plane, then it is taken as negative, or you can choose your own sign convention according to you. But in most of the case, we take if the torque is out of the plane as positive, into the plane as negative. Okay. So you have to remember how to find out torque about a point. Clear? So torque is a vector quantity In vector form, we can write tau vector equal to r cross f, or in magnitude tau mod equal to r mod f mod sin theta, or this can be written as r perpendicular into f, or we can also written as r into f perpendicular. Clear? And its direction will be obtained by right hand thumb rule. Okay, clear? So this is how we can find out the torque of a particle about any point. So what is the torque of a particle about an axis? So we are going to torque about an axis is the component of torque along the axis. Clear? For example, if this is the point, this is the position vector, and here I am applying the force F. This is the position vector R. So about this point O, the torque will be like this. This is the direction of R vector, this is the direction of F applied. So the torque will be along R cross F out of the plane. Okay. If I am taking the axis of rotation as this, let this will be the axis of rotation. So the torque about this point O will be how much? R cross F. But if I am taking the axis of rotation like this, okay, if this is the axis of rotation and I want to find out the torque along this axis Z dash. Clear? So if I am asking the torque due to this force F about this point O is, can be written as tau about point O in vector form, can be written as R cross F. Due to this force F, the torque about this point O is defined as R cross F. But if I want to find out tau mod, this is the magnitude I am writing. So tau mod about Z dash will be equal to how much? So the torque about this axis Z dash is not equal to R cross F. It will be what? It will be the component of this torque which will act along this axis. So as I am getting the direction of torque is out of the plane, so here the torque is like this, which is perpendicular to this axis. So there is no component act along this direction, because as the complete torque is perpendicular to this axis, so there will be no component which will lie along the axis. That's why in this case the torque about Z dash will be 0. Because what is torque about an axis? You have to remember it. The torque about an axis is the component of the torque along the axis. In this case, there is no torque along this axis. Clear? That's why torque about the axis Z dash will be 0. But if I am taking another axis which is into the plane, that is Y. Here another axis, Y axis, which is into the plane. So again, what will be the torque about this axis Y? As here the torque is R cross F, which is perpendicular to this plane, and I am considering this axis Y, then the torque about the axis Y will be again R cross F, because the complete torque is lying along this axis of rotation. So if I am want to find out torque about the axis Y, it will be again equal to R cross F. Clear? So if the torque has a component along the axis, then that is known as the torque along that axis. If there is no component of the torque along the axis, then the torque about that axis will be 0. Clear? It's an important point you have to remember. But torque about the point is what? The position vector of the point of application of force with respect to the point about which we want to find out the torque due to that applied force is given as R cross F. Clear? Or the perpendicular distance of the point of application of force to the point about which we want to find out the torque, or the component of force which is perpendicular to the position vector. Clear? So it's a vector quantity. It has direction which can be obtained by using right hand thumb rule. Then how to find out torque of a rigid body? So for example, if it's a rigid body which is rotating about an axis z dash having moment of inertia I and it's rotating with angular acceleration alpha. Clear? So here I is equal to what? Moment of inertia of the rigid body, and alpha equal to what? Angular acceleration of the body. So torque acting on the body is defined as I alpha. Clear? Because as in case of a particle, if F is the force, then it can be defined as mass of the particle and acceleration of the particle. This is in case of linear motion. So in case of rotational motion, force is what in case of linear motion, torque is that in rotational motion. So tau is equal to I into alpha, and we know moment of inertia is same as that of mass in linear motion, and alpha is same that of acceleration in linear motion. So for a rigid body which is rotating about an axis has moment of inertia I and angular acceleration alpha, so its torque can be defined as I alpha. Clear? So you have to remember, and the direction of torque will be along the direction of alpha. Clear? So what is unit or dimension of torque? As we already defined, tau equal to Rf. R is the perpendicular distance from the point of application to the point about which I want to find out torque, or this can also be written as R into F perpendicular. So its unit equal to Newton meter or Dine centimeter in CGS, and dimensional formula will be how much? Same as that of work, that is M1 L2 T minus 2. Clear? You have to remember this torque has unit and dimension same as that of what, or this can also be written as joule, and or same as that of work or energy. Okay. So next we have to study what is couple. So what is couple? It's a pair of force. Okay, it's a pair of force having same magnitude but acting along opposite direction in different line of action. Okay, so it is a pair of force having same magnitude but acting along opposite direction in different line of action. What is line of action? Line of action means the two forces are not lying on a same line, or these two forces are not collinear. Okay, for example, here I am considering here is a force which is acting along rightward direction, that is F1, and another force which is acting along this direction, that is F2. These are two forces. The line of action of this force is this, and the line of action of this force is this. So these two forces are acting in opposite direction along different line of action, and here I can write the magnitude of F vector is equal to the magnitude of F2 vector. Then in this case, according to the definition of couple, as two forces equal in magnitude, opposite in direction, act along different line of action, then these two forces are known as couple. Okay, couple means a pair. So these two forces are known as couple, and these two forces are cause of producing turning effect, or these force can produce torque. Okay, so what is the perpendicular distance between them? So we can write, this is an example of couple. Here we can also write the moment of couple produces torque. Okay, the moment of couple produces torque, and here you can write tau is equal to defined as magnitude of either force into perpendicular distance between them. Okay, so torque can be defined as the magnitude of either force into perpendicular distance between them, or we have to remember the moment of couple produces what? Torque. So here the magnitude of either force as F1 equal to F2, so I can write F into what is the perpendicular distance between them. If the distance between these two lines be, or the point of action be R, and this is the angle theta. So if this distance is r and this angle is theta, so the perpendicular distance between them will be this one. This is 90 degree. So if this is r, this angle will be theta, it will be r cos theta, this will be r sin theta. Clear? So from this point to this point, the perpendicular distance between these two forces is r sin theta. So I can write tau is equal to magnitude of either force, as both the force of same magnitude, I am taking F into r perpendicular. What is r perpendicular? That is r sin theta. So this is defined as what? Torque due to this couple. So to produce a torque, a pair of force is necessary. A single force can never produce torque. Okay, to produce a torque, a pair of forces is necessary, and that pair of force must be equal in magnitude, opposite in direction, and acts along different line of action, and that particular pair is known as what? Couple. Clear? So moment of couple produces what? Torque. This can be defined as, this is the formula, or mathematically it can be written like this. Clear? So we have to remember what is couple, and the moment of couple produces torque, and what is the formula for torque in terms of couple? That is magnitude of either force into perpendicular distance between them, which can be written as Fr sin theta. Okay. So one important point you have to remember: to produce torque, a pair of forces is necessary. A single force can never produce torque. Clear? Then if the torque has no component along the axis of rotation, then it can't produce turning effect. If the torque has no component along the axis of rotation, then that torque can't produce turning effect. But in case of, if there is any component of the torque which is act along the axis of rotation, then the torque is responsible for the turning effect, or it can create rotational motion or turning effect in the body. Clear? Okay. So this is all about torque and couple, which is same as that of what? Force in case of linear motion. And for a rigid body, the torque can be defined as I alpha, where I is moment of inertia of the body and alpha is what? The angular acceleration of the body. Okay. So next we have to find out what is angular momentum. This is defined as L, capital L vector. So as we already studied, in case of linear motion, the linear momentum is defined as the product of mass and velocity of the particle. So in rotational motion, what is angular momentum? So this is can be defined as, if here is a particle of mass m which is move along this direction with certain velocity v. Okay. So the angular, it's a linear momentum, we can find out the linear momentum of this particle. Let it be A. So linear momentum of A small p vector is equal to mv vector, we already know. But if I want to find out the angular momentum of this particle about this point O, okay, the angular momentum of this particle about this point O, where the position vector of the particle A from point O is r vector. Clear? Then the angular momentum of the particle A about the point O is defined as, let the angular momentum about point O is defined as the position vector of the particle A and cross product of linear momentum of the particle. Clear? So the angular momentum of a particle which has linear momentum p, that is mv vector, about a point O which has a position vector of the particle r vector, is defined as this much. Or this can also be written as the angular momentum of the particle O about O is defined as, let it be LO of A is defined as what? R cross p. This can be written as r vector cross, in place of p I can add m into v vector. So this can also be written as r cross v vector into m. So the angular momentum of a particle about a point is defined as the cross product of position vector of the particle with respect to that point and the linear velocity of the particle, which is multiplied with the mass of the particle. Clear? Or this can also be simply write as the L of O about A mod can be defined as r v m sin theta, or this can also be as the perpendicular distance r perpendicular mv, or this implies you can write L of O mod can be written as r m v perpendicular. Clear? So you have to remember this formula. That means the angular momentum in vector form can be defined as like this about this point O, or by magnitude if this is the direction of velocity and the direction between the position vector and the velocity be theta, then the perpendicular component of velocity to the position vector will be this one. This is the v perpendicular. So about O, this can be written as r m v perpendicular, that is this component of velocity. Or else if this is the velocity, we have to take the direction of r which is perpendicular to the direction of velocity. So for this I can write this is the direction of r perpendicular. So the angular momentum about this point O can be written as what? R perpendicular mv or r mv perpendicular, or in vector form it can be written as r cross p or r cross v into m. So this is how we can find out the angular momentum of a particle which has linear momentum this much about a point O. Clear? So this is also a vector quantity. So this is also a vector quantity, it's a vector quantity. Okay, because the L vector is defined as r vector cross p vector. Okay, direction can be obtained by using right hand thumb rule. Clear? Then its magnitude unit will be how much? R cross p. So this can be done meter mass into velocity. So its unit will be how much? Meter. Momentum has mass into velocity is meter per second. So this can be kg meter square per second. Clear? And dimension formula m1 L2 t minus 1. Okay, meter, this is m into v, that is meter per second into mass. So kg meter square per second is unit, or gram centimeter square per second in CGS, and dimension m1 L2 t minus 1, because this can be written as L vector mod is equal to distance position vector r vector mod into mass into velocity. So mass is kg, this is meter, velocity is meter per second, so kg meter square per second or gram centimeter square per second, and has unit m1 L2 t minus 1. Okay. So how to find out the angular momentum of a rigid body? Same as that of linear motion. Here you can write the angular momentum of a rigid body having moment of inertia I and angular velocity omega is defined as L vector mod is equal to I omega, or this implies L vector equal to I omega vector. Okay, so for a rigid body, if this is a rigid body which is rotating about this axis with omega and this body has a moment of inertia I, then the angular momentum of this body about this axis is defined as what? I omega, or in vector form L vector equal to I omega vector. Clear? So this is how we can find out the angular momentum of a rigid body which has moment of inertia I and an angular velocity omega, which is same as that of linear momentum in case of linear motion. Clear? Next, what is conservation principle of angular momentum? So as we already studied in case of conservation of linear momentum, for an isolated system the total momentum is constant or the change in momentum is zero. What is isolated system? If in that system there is no external force acting on it. So in case of conservation principle of angular momentum, so if the system is isolated, that means there is no external torque acting on the system, then the total angular momentum of the system is constant or the change in angular momentum is zero. Clear? So this state what? For an isolated system, if tau external is zero, that means no external torque is acting, then the angular momentum is constant or the change in angular momentum is zero. Clear? So you have to remember this. For conservation principle angular momentum is what? For an isolated system, external torque is zero, then the angular momentum is constant or change in angular momentum is zero. So we can prove this. If tau is constant, then same as that of linear motion, we know what is Newton's second law, that is F vector is defined as ma vector, or we can write F vector equal to the change in momentum with respect to time. So F vector equal to dp by dt. So here also we can establish the relation between angular momentum and torque. So how angular momentum and torque is related? So let's check. We already know that tau is how much? R cross F. And what is angular momentum? This is defined as R cross P. Okay. So by differentiating this, we will get dl vector by dt vector, which is equal to how much? D by dt of R cross P, or this can be written as dr vector by dt cross P plus R cross dp vector by dt. Okay, so this will be how much? dr by dt is what? V cross P plus R cross dp by dt is what? Linear force F, which this is equal to dl by dt. So from this we can write V cross P. So this implies dl vector by dt is equal to V cross, in place of P momentum I can write m into V vector plus r cross f. So here V cross V tends to 0. So this implies dl vector by dt equal to r cross f. What is r cross f? We already know it is tau. So from this we will get the rate of change of angular momentum with respect to time is defined as torque, tau. Clear? So as here we already discussed for an isolated system, tau external is 0. So this implies I can write what as tau external is 0. So dl vector by dt equal to 0. And if the derivative of L with respect to time is 0, this implies L vector must be constant or the change in angular momentum equal to 0. Clear? This is what known as conservation principle of angular momentum. So if change in angular momentum is equal to 0, so for a rigid body, I can write as change in angular momentum equal to 0. So for a rigid body, I1 omega 1 must be equal to I2 omega 2, or this implies I1 by I2 equal to omega 2 by omega 1. Clear? It's an important relation you have to remember. For a rigid body, if the angular momentum is conserved or the system is isolated, that means external torque acting on is 0. Then I1 by I2 equal to omega 2 by omega 1. This is known as what? Conservation principle of angular momentum. Okay. So when initial angular momentum must be equal to final angular momentum. Okay, so this is how for an isolated system the total angular momentum is conserved. So what are the examples of conservation principle of angular momentum? So in case when a person or man is holding two weights on his hand and he is standing on a rotating disc or rotating table. So if the man is folding his hands like this and stretching it like this and holding by two weights, he can change the moment of inertia of its own, because when he bring his hand close to his body, the weight or the mass he hold in his palm come close to his body, so the distribution of mass changes, so the moment of inertia of the body or the system decrease, and when he expand his hand or stretch his hand, the mass distribution increases, so the moment of inertia increases. But as there is no external torque acting on the system, so when the man fold his hands or decreases the moment of inertia, the angular velocity of the system, because the man is standing on a rotating table, so he is also rotating, so the angular velocity of the system will increase to keep the angular momentum constant. And when the man stretches his hands, the mass distribution increases, so moment of inertia increases, so the angular momentum of the system decreases, because it want to always maintain the angular momentum constant. So I when increases, omega decreases, when I decreases, omega increases. So this is the example when due to conservation of angular momentum the man can keep rotating. Okay, again when cat or dog jumps from a certain height, they stretch their body along with their tail to increase the moment of inertia, so that they can land safely to decrease the angular momentum. Clear? Because the angular momentum is constant, so when they jump by stretching their body parts, the mass distribution will increase. If mass distribution will increase, the moment of inertia will increase, so the angular velocity will decrease to maintain constant angular momentum, so they can land safely. Clear? So these are some examples of conservation principle angular momentum. You can get some more examples from different books. Okay, so this is how angular momentum is conserved for a isolated system. Okay, so next we have to discuss, we already know what is center of mass. It is an imaginary point where total mass of a rigid body is supposed to be concentrated. It may be lie inside the body or outside the body. Same as that of center of mass, there is another point where total weight of the body is conserved. So that is known as center of gravity. Okay, what is center of gravity? Or this is a CG. So center of gravity is what? It is an imaginary point of a rigid body where total weight of the body is supposed to be concentrated. Okay, what is weight? We already know weight equal to how much? M into G. Clear? So it is an imaginary point of a rigid body where total weight of the body is supposed to be concentrated, and you have to remember, for small objects center of mass is equal to center of gravity, but for very larger objects like a bar of 1000 kilometer height, the center of mass and center of gravity changes, because as the height is very large, the value of G for different level will be different. So the center of gravity shifts different places in comparison to the center of mass. But for small objects like me, you, and small short height buildings, the center of mass and center of gravity mostly lie at the same position. Clear? Because the G remain constant for very small height, that's why center of gravity and center of mass lies at the same point. But for very larger objects like Burj Khalifa or Eiffel Tower, when the height is very high, in that case the center of mass and center of gravity changes from each other. Okay, so what is center of gravity? It is the point where total weight of the body is supposed to be concentrated, and center of mass is the point where total mass of the body is supposed to be concentrated. Clear? Okay. So this is all about center of mass, center of gravity, moment of inertia, torque, couple, angular momentum, and the conservation principle of angular momentum. Okay. So this is all about your rotational dynamics that was in your syllabus. Okay. In next class we will discuss further. Thank you.